Hello, in this video we're going to talk about Gibbs energies of formation and how we can use that to calculate the Gibbs free energy change for a reaction at standard states. So here's what we're trying to calculate, the standard free energy of a reaction. So this is delta G for your reaction when you have 1 molar or 1 bar, depending on whether you're in solution or a gas. And this number is constant for a reaction. And then you can use this to calculate some useful things about your reaction. So we can calculate these from the standard free energy of formation values. And so these are defined as the free energy change when you start from elements and make 1 mole of the compound under standard states. So let me scoot this up here. So for example, if you have some generic reaction here, you can take final minus initial and use the numbers that you have. So we'd have the standard free energy of formation value for compound C, and then you multiply it by its stoichiometric coefficient, which is the lowercase thing here. And then the same is true for D. You take the delta GF for that, the standard free energy of formation, and multiply it by its stoichiometric coefficient. And then you subtract that from the sum of the two reactants. And so we simplify this into this format, and this is what you'll see on your info sheet, is how you make this. And you have to know this piece, that when you see this formula, you're going to add the species together and multiply them by their stoichiometric coefficients. Now, this is in analogy and very much the same thing as what we did with enthalpy, right? We create some reference state, and this is arbitrary. We just find it convenient to set free elements equal to 0, and that's our reference state. And then from there, you can find either the enthalpy change or the free energy change to form some compound, and then we call those numbers delta G naught F or delta H naught F because we're at standard states here. And then we can use these values to figure out, okay, if you go from one compound to another, what is the change for that type of reaction? So in contrast, when we're talking about the entropy change for a reaction, delta S naught reaction, we can use absolute entropy to calculate these things. And there's no reference required. There's no delta from your reference state, and there's no F for formation. You can just use the entropy values. Ultimately, you use them in exactly the same way, regardless of whether it's formation or not, but we might as well tell you what this means. So, irrespective of which one you have, you just find the change for your reaction by taking products minus reactants, multiply everything by its stoichiometric coefficients, and you're set. Another little nuance is that standard state does not imply a temperature. It tells you that pressures have to be 1 bar for gases or 1 molar for solutes, but there's no temperature required here. However, we have to pick a temperature when we're going to make this table of values for entropy, enthalpy, and free energy, and we pick 25C. So ultimately, when you use these values from the table to find some sort of change for your overall reaction, you're going to get an answer that comes out at 25 Celsius. So then we're limiting ourselves a lot to then what numbers we can calculate because we're at 25C. So from there, delta G naught for the reaction is going to vary wildly with temperature because equilibrium position changes with temperature to a large degree. But delta H naught reaction, delta S naught reaction, those are roughly constant with temperature. I mean, that's not a great approximation that they're constant, but it's okay. And so you can use that approximation in this course if you so need. So for elements in their reference state, which is the lowest energy states, so for example, O2 gas, delta H of formation and delta G naught of formation are both 0 because that is the reference state, but this absolute entropy doesn't equal 0. So if you look down in this table here, none of these entropy values are 0, but say delta H naught F, delta G naught F, these are equal to 0 when you have a pure element, or you have, say, carbon in its lowest energy state, things like that. All right, ultimately, you got a table. You can pull numbers out of it and do your math. Now, do be aware that sometimes in a problem, we might not tell you that the enthalpy or free energy change of formation is 0. So you may have a problem where this number is not given to you, and you should know that that's equal to 0 because this is an element in its most stable state. Okay, so let's do this to do a problem. We're going to burn benzene again, and here's the values that you pull out of a book or a table or something. You have a big appendix in the end of your book with a whole bunch of values in it. And so we're going to take the value from here for the carbon dioxide, and we're going to multiply it by 12. So there's the 12, right? We need to multiply the free energy of formation by 6. That goes here. Then we're going to subtract from it 2 times the free energy of formation for the benzene here. And then we don't even have to include the oxygen because it's equal to 0. So then you just compute and you get your answer. So the ultimate outcome here is pretty straightforward, right? There's a bunch of kind of nuances behind why it works. But ultimately, you got the values, use the equation. Don't forget the coefficients. Don't forget to handle the negative sign correctly, because if there were 2 reactants, we'd have to wrap this whole thing in brackets. You do that and you're fine. So that's all I got for this video. Thanks for watching.